Okay, you guys, this is section 14.6 notes. This is about reaction mechanisms. Make sure that you are following along in your book. So looking at the figures, the bolded words, reading through the sections to help your understanding. So usually for a reaction, we'll write an equation. And an equation just shows what are you starting with and what are you ending with. It doesn't tell you any of the information about like how the reaction proceeds, what we see in the middle. So in order to kind of figure out how does a reaction actually occur, we have to look at a reaction mechanism. So the reaction mechanism actually shows like step by step what happens in order for this reaction to occur. So when we talk about rate, we talk about the orientation and the activation energy. This is going to help us look a little bit more at that kind of orientation piece of like what things need to go together in order for this reaction to actually occur. So reactions can happen in different ways. There are some reactions that happen all at once. The simplest reactions happen in just one step. Most, though, occur through several discrete steps. And when we talk about discrete, we're talking about like specific things that have to happen in order to make the products. So whether it is a one-step process or it's a two-step or a three-step process, each of those steps is known as an elementary reaction or an elementary process. So when we think of like elementary school, we think of kind of like basic, the lowest we can break it down. That's what an elementary process is. So when we look at those elementary reactions or that process, we can look at the molecularity of each process. So molecularity is just a way of saying we're going to look at how many molecules are involved in the process. And we have kind of talked about this with orientation. If there's two things and there's only one way for them to kind of interact with each other, that's going to happen faster or easier than if there are three things that have to interact or even four things that interact. And so we can look at the molecularity as basically a measure of how many things are involved. So something that is unimolecular, uni meaning one, has just one thing involved in the reaction. So it's probably some sort of like decomposition where you've got one thing and it maybe breaks apart into multiple products. When you have an elementary reaction, so when you've broken it down to that lowest point, you can use the balanced equation to determine the rate law. So this is kind of another way to determine a rate law. We looked at data, we looked at the graphs, but you can also look at the elementary reaction. So we have three ways to determine the rate law. In a unimolecular reaction, since there's only one thing, the rate law is only going to include that one thing, and it's going to be a first order. A bimolecular, meaning two, is going to be second order. And there's a couple of ways that could happen. It could be two of the same thing needing to collide. So then our rate law would be that squared. Or it could be two different things that need to collide. And then it would be first order in both of those. Okay, this kind of goes on. A termolecular, tertiary, three. It can be three of the same things that need to collide. So it would be one thing to a third order, or it could be, two of the same, one different, or they could all be different, and that's going to affect the rate law. So we're going to practice determining that rate law in our next couple of slides. You guys come back to this here if you are wondering how to determine a rate law for an elementary reaction. Okay, so first let's look at molecularity. So again, you guys, molecularity is just basically saying how many things are involved. How many reactants do you have? So in this one, I've got my plus sign, which tells me I have two different things. So this is going to be bimolecular, meaning two molecules that are involved. If this were an elementary process, our rate law would be rate equals the rate constant times the concentration of NO and the concentration of the Cl2, because it's just one of each, by meaning it's going to be second order overall. This would be kind of like the easiest type of reaction. However, most reactions proceed in multiple steps, which means that we start with our reactants and then something happens, maybe something else happens, and finally we get to our products. So those things that are formed in the middle that we don't necessarily see in a balanced equation are intermediates. So intermediates are things that are formed and then used up. So they cancel each other out in the overall reaction, which is why we don't see them when we do our balanced equations. So if this is the proposed mechanism for how ozone converts into oxygen, they're saying that it is a two-step mechanism. So we can do a couple of things. First, we can describe the molecularity of each elementary reaction. So we're going to say this is reaction 1. So first this happens, then this happens. Okay. When we describe molecularity, we're only looking at the reactants, what things need to come together. So reaction 1 has just one reactant, so it is unimolecular. And reaction 2 has two reactants, so it is bimolecular. Okay? So next, we can write the equation for the overall reaction. So this is similar to Hess's law. When you have the steps, if something appears on both sides, they cancel out. Otherwise, bring everything else down. So I see that in my reactants, I have an O, and in my products, I have an O. And so those cancel. I see two O3s, but they're both on the reactant side, so I'm going to bring that down. So I've used all my reactants, and then I see 1 plus another 2 O2s, and again, they're both on the product side, so they can't cancel, they add. So that's 3 O2s. So this is our balanced equation. So it's showing that 2 ozones react to form 3 oxygen. So that tells us kind of what we start with and what we end with. But again, it doesn't give us any information about how that happens. One last thing that we can do with this kind of process here is we can identify an intermediate. And again, you guys, the intermediate is going to be the thing that was formed maybe in the first step and then used up in the second step. So for this one, it's what cancels out. That was our oxygen gas, not our diatomic oxygen, just our single oxygen. And we know from previous lessons that oxygen wants to be diatomic. So this would be super fast. We would have the oxygen and then it would be gone immediately. So if it's an elementary process, we can find the rate law just from the balanced equation, looking at if it's unimolecular or bimolecular. But if it's a two-step process, we have to go through a different avenue in order to determine the rate law. So in multi-step mechanisms, one of the steps is going to be slower than the others. So either it has a higher molecularity, which is going to change that orientation factor, A, or maybe it has a higher activation energy. So there's something about that reaction that is making it slower than the other one. And so the overall reaction can't occur faster than that slowest step. So in a reaction, the slow step is called the rate determining step. Okay, so I know that most of us have maybe been driving on the highway. The example below is a toll plaza, which we don't have really in Minnesota, so maybe if you've been out of state. But let's say you're driving down the highway and there are like two cars going below the speed limit right next to each other, and you can't get around them. So you can't go any faster than those two slow cars. You can try and get around them, but they are blocking the entire thing, which is so frustrating, but that means that you have to slow down. Reactions are the same way. If there's one reaction that wants to go really, really fast, but the other step is slow, it can't go any faster than that slow step. So that slow step acts like those slow cars and block this from happening. Okay, so we're going back to that kind of initial equation that we looked. We're going to look at another equation here. So this one is going to have a slow initial step. So this is our overall reaction, okay? So this is the overall. It tells us what we're starting with and what we're ending with. We know that this is bimolecular. So if this was an elementary reaction, meaning this happened in just one step, our rate law would be rate is equal to the rate constant, NO2, CO. Okay, so if it were elementary, this would be our rate law. Experimentally, when we find this, so either by graphing the data or by looking at different concentrations, we found that this is actually the rate law. So it is second order NO2. So what that tells us is that the carbon monoxide is necessary for the reaction to occur. Obviously, if it's a reactant, we have to have it. But the rate of the reaction does not depend on it. So it is zero order in carbon monoxide. So because the actual rate law doesn't match if it were an elementary process, that means that this occurred in 2 or maybe 3 steps. So now we have to work at kind of deciding what is the actual process. And so scientists come up with kind of different ideas of what this might look like. So this is a proposed mechanism for this reaction. So let's go ahead and just make sure that things cancel out. So when we add these together, let's see. So I've got NO2 and NO2. I don't see any of that in the products. NO3. Okay, so I see NO3 in the products and in the reactants. Oh, you're right. 1 NO2. One of these are going to cancel. Okay, everything else is unique. So ends up being NO2 plus CO gives us NO and CO2. Okay. Notice over here, you guys, that we have these slow and fast. I will always give you that information. You can't tell just by looking at it which one is the slow step and which one is the fast step. So in this one, since NO3 canceled, it was made in the slow step and then used up in the fast step. NO3 is our intermediate. And because our slow step is our rate determining step, only the NO2 determines the rate. So CO is in the fast step, which means that we need it in order for this to occur, but it doesn't determine the rate law. So now, once we know kind of the proposed mechanism, so these are both elementary reactions, we know which one is the slow step, we can determine the rate law. So the slow step is bimolecular, so rate equals K. And then it is NO2, and there's 2 of them, so it's going to be second order, which matches from the last slide what the proposed rate law, or what the rate law we determined from the data. Okay, So let's look at one more of these examples, and then there are a few examples in your book assignment as well. So the decomposition of nitrous oxide, N2O, is believed to occur by the two-step mechanism above. First, we're going to write the equation for the overall reaction. So we are going to cancel out our intermediate. So we start with N2O, creates N2NO, and then that and more N2O and oxygen react to form our N2 and O2. So the thing that I see in the reactants and products is my oxygen gas. So that is going to be our intermediate. And everything else is brought down. So I'm going to write it down in part A. So I have 2 of the N2Os. And then I have 2 N2s and 1 O2. Those are all gas. Okay, so that's my overall reaction. Now, since it's a two-step process, I can't determine my rate law from the overall. I have to determine it from my elementary steps, and specifically my slow step is my rate determining step. So this is a unimolecular because I just have one reactant, which means my rate law should be the rate equals K, N2O, I don't rate the 1, so that is my rate law. Now, just like the other ones, if I was given some data for the rate and the concentration, then I could plug it in and I could solve for my K value in the same way that I have solved in other steps.